I've broken down Chapter 4 into 3 separate parts to make it easier to learn. So Part B is going to be about residual analysis. Let's review what a residual is. The difference between the values observed for y, given different x values, minus what was predicted with those same x's. So it's a form of error, in other words. And we always like less error. The assumptions are things that we need to practice a little bit more before we move on. The mean of the residuals is always 0. Most of you got that on the first exam. The idea of severe outliers we're going to practice a little bit more though. And then the residuals should be normally distributed. Again, if there are no severe outliers, that's probably true. Now we have a new term for randomness. When we look at the residual plot, we should see what looks like a shotgun target. In multiple regression, we call that homoscedasticity, meaning that we have constant variation. It remains the same across the different values of the residuals. So we'll learn what to do if they don't have homoscedasticity in the next slides. Checking the residuals, the first assumption is always true, that the mean of the residuals will be 0. Then again, we look under studentized residual column heading, and we look for values that are greater than the absolute value of 3. Those are considered severe outliers, and we must hide and exclude them. Values under studentized residuals that fall between 2 up to the absolute value of 3 are considered suspicious, and often I make a note of those, especially as they approach the absolute value of 3. Then, once there are no severe outliers, we'll consider our data normally distributed. Now, the new term, homoscedasticity. If you look at the residual plot and you see a greater than, less than, or a combination that almost looks like a football shape, then that is displaying heteroscedasticity, or changing variation. We don't want to see that. That makes our model less accurate. So we'll do something in order to fix that. So here's where we look at the outliers. We go to studentized residuals in the jump output, and lo and behold, observation 1 is a severe outlier. Its value is negative 3.02. So we go over to the left-hand side, right-click on observation 1 there, and say hide and exclude in jump. That then puts these little symbols there saying that we are not going to use this observation when we rerun the data. Then look at observation 2, negative 2.008. That value is suspicious. So I do not have to remove it, but I might make a note of it. I go on down the column and I don't see any other types of outliers. So now we'll proceed with our next look at the residuals. So now we look at our graphs of the residuals. On the left-hand side, you'll notice that you have changing variation, which is called heteroscedasticity. Do you see how on the end where the residual on the x-axis is 50 to 60, there's a little bit of variation. But as we go out to 70, 80, and 90, that variation gets wider and wider. That gives us this sort of less than sign look. So that's heteroscedasticity. And one of the ways we solve that is we transform y. We try the log of y first as a typical solution. If that doesn't work, you can take the reciprocal of y. We can try sines and cosines, but we're going to stick to the log of y as our standard fix. And so on the right-hand side, when I transform y and rerun the model with that rather than the regular y, I get this more homoscedastic type of chart where I have more constant variation. This is the look we want on the right-hand side. So in this model 2, I've removed the outlier and I have homoscedasticity. This is what I want to see. When I go to compare models, if I said which model does the best job of predicting y, look at your root mean square error up under summary of fit, and you find 121.34 in this model. If model 1 had a root mean squared error of 143, then model 2 would be the better model. It has a smaller root mean squared error. Think of it like this. If error is bad, you want to make a smaller amount of errors. If alpha is 0.10, when we look at which variables to keep in the model, we go under the probability of t and look at each individual variable. We compare prices p-value, less than 0.0001 to 0.1, and it's a good predictor. Competition's p-value, 0.07 is less than 0.10, it would be considered good. And style, less than 0.10, it's a good predictor. And so is comfort.